So last time we're talking about linear response theory. So we claim that our Hamiltonian H is constructed out of a free part, not a free part, time-independent part, plus a time-dependent perturbation. Okay? And then using this interaction theory and expanding everything to linear order in up to the linear order in V of t. By the way, let me write what this V of t is. V of t is some integral over space, because this is a class in field theory, times an operator, which is the field operator, times some f of x and t. And we find that phi of x and t minus phi I of x and t, where we said that the interaction picture is evolving only with h naught. So this is kind of the dynamics that doesn't interest us. So the difference between these two is given by minus I, the integral dt prime, the integral dx prime, times chi of x minus x prime, t minus t prime, f of x prime and t prime. And this chi of x, let's call it psi and tau, is I theta of tau. Sorry, no I here. No minus. This comes with a minus. Sorry, this comes with a minus, and then this cancels out, and then we get that this guy is equal to phi I of psi and tau, phi of 0 and 0. Here I'm assuming both translational and temporal invariance, Galilean invariance. Then we also discussed this issue about dissipation. So we claim that dE to dt, which is the amount of the power that this field is pumping into the system, okay, is given by d to dt of h, which I claimed was the h to dt. Okay, and this, I'll explain this now in a moment, because what Oz said is correct, but let me just explain it explicitly in a moment. And therefore, it only gives us the derivative of this v part. So we get the integral from 0 to L dx f dot of x and t times the expectation value of f of x, f of x, at time t. So to be more explicit, let me write it like this. I can write it psi of t, let's call it. It's like the wave function, the field wave function, say phi of x psi of t, psi of t. This is what we mean. And this, basically, this is something we can calculate up to linear order, up to linear order. We get that this thing is some integral of dx f dot phi I, which is like the trivial part, which because phi I has to be oscillatory, this typically doesn't contribute a constant power term. Then we have integral dx prime dt prime f dot of x t chi of x minus x prime t minus t prime f of x prime and t prime. So let me explain this transition here for a moment. The idea would be that d to dt of h would be actually like writing psi of t dh to dt psi of t plus d psi to dt h psi plus psi h d psi to dt. This is like the full derivative. But the issue is that d psi to dt, right? This thing is exactly 1 over I h bar h psi, right? And d psi to dt is therefore equal to minus 1 over I h bar psi h. Okay? And therefore these two terms cancel. But this is exactly just another way of writing exactly what Oz was saying last time, that the non-direct time dependence of an operator comes from its commutation relation with Hamiltonian, and in this case Hamiltonian doesn't generate its own dynamics. Okay? So that's that. And then what we saw here is we defined this quantity chi double prime, okay, which is 1/2 phi I of x and t phi I of x prime and t prime, and therefore we get that chi is equal to 2 times I theta of t minus t prime times this chi double prime. Okay, that's what we get. Today we're going to see that this chi double prime is actually the Fourier, like in Fourier space. Let's say I transform chi double prime and chi to Fourier space, then chi double prime is the imaginary part of chi. And then using this result, we saw that the dissipation, that is d to dt, we saw that this d to dt if we average it over a cycle, or average out the terms that are time, that are not, that don't average out in a cycle, then we get this chi double prime of omega. So what it implies is that this chi double prime that we've defined, right now I didn't show you yet that this is the imaginary part of chi in Fourier space, but I did show you that this chi double prime is responsible for dissipation, and today we're going to close the circle and show you indeed that it is the imaginary part of the susceptibility, and that shouldn't surprise you, because as you know, what is the best intuition? For example, you could think of like a response of a dielectric medium, for example, which gives rise to an imaginary refractive index, right? So if I plug that in the evolution of the wave equation, that causes decay, for example. Okay, so it's not new to you that when a response function has an imaginary part in frequency, in its frequency components, that implies a decay, okay, or a lossy medium. Then the next step was we saw the FDT, the fluctuation dissipation theorem. So fluctuation dissipation theorem, we defined another function, which is S of x and t, which is delta phi of x and t, delta phi of 0 and 0. Again, I'm assuming translational invariance, and this delta phi here is not this delta phi. Okay, it's not the same thing. This is equilibrium. Okay, so this phi is just a phi minus its average. So there is no interaction picture and no funny business. There is no V, none of that. Okay, it's just the good old fluctuations that you know and love. Okay, and for these fluctuations, we found that S. Okay, so here, okay, so this is kind of at thermal equilibrium. Maybe I should write at thermal equilibrium. We found that S of x minus x prime and omega is equal to e to the beta omega S of x prime minus x and minus omega. And this implied that we can get x double prime of x minus x prime omega by 1/2 1 minus e to the minus beta omega S of x minus x prime and omega. And this is known as the fluctuation dissipation theorem. It's a direct connection between the dissipative part of the response function in a drive, which is the response to the drive, and the equilibrium fluctuations. Okay. And now the last thing where we stopped last time was the analytic properties of chi of omega. Okay, or I would even call it chi of z. So I'm analytically continuing z to the entire complex plane, and I want to discuss the analytic properties. So you guys were clever clogs and gave me a hard time. So let's discuss. The point was this. So I was claiming that due to causality, okay, this condition holds. Okay? So that implies that if I want to write the Fourier space, if I want to write this chi, okay, let me just write it like this. So I can also write this 0 in a very sophisticated manner, which is the integral from minus infinity to infinity, the omega over 2 pi, chi of omega e to the minus omega t. And my claim was that because so this is omega, and here I can put the imaginary part of this z. Okay, then I'm basically performing this part of the integral. But my claim was I can always close the contour here, and because of this contribution here that gives an exponential decay, this integral, and I'm assuming that chi of omega doesn't diverge, exponentially at infinity, then this thing has to be 0, and therefore I can rewrite this as an integral over a closed contour, dz over 2 pi, chi of z, e to the minus I zt. And from here I concluded that chi of z is analytic in the upper half plane when where imaginary z is larger than 0. Okay, now you guys claim that it's possible to find situations where this doesn't work. So do you still believe that? You checked that or what?
I didn't check it, but I thought about it.
Okay.
If the lemma של Jordan, it's true in the opposite way, so we can conclude that it's okay. But, I didn't really check. I thought about it.
Okay, so I don't have rigorous proof, so I'm not a mathematician, but I can give you at least we can try. What we can try is we can say, let's assume that chi of omega is say some g of omega, g of z. Okay, and then I'm gonna give it 2 poles. Okay, 2 poles that sit somewhere in the upper half plane, and what I demand is that the residue of this integral overall vanishes in this contour. So what that implies, it implies that if I look at that, it's basically that g of z1 e to the minus I z1t divided by z1 minus z2 needs to be equal to g of z2 e to the minus I z2t divided by z2 needs to be equal to z1 minus z2, where I flipped the sign here because I switched sides. Okay?
Mm-hmm.
So you agree about this? It's agreeable? So what that implies that the ratio g of z1 to g of z2 needs to be equal to e to the I z1 minus z2 times t. Okay?
Yes.
Now, yes, you can find a g that will satisfy this for a specific t, but not for any t. Right? Now, this is of course not rigorous proof because I don't know about like fancy branch cuts, whatever. But
I think there is the opposite theorem to Jordan, but it only happens if in every closed loop in this domain you have a zero integral. That's
so on every. You mean I can shrink it to 0 or something? That's what.
Yeah, or specifically, let's say that you have a pole, then you don't really have poles because if you have a pole, then around it you should have integration 0. But if you have a pole, it can't happen. So you don't have poles.
So how is it a contradiction to Jordan? In what sense?
No, it's not a contradiction to Jordan. I'm saying that you assume the specific structure.
Yes, yeah. I know. I was saying I'm not a mathematician. I'm just giving you intuitive arguments. But
yeah, so it can't be of that structure.
It what? It can't be of this structure.
Yeah, but it may be of a more complicated structure. But maybe we don't care.
No, but let's discuss this for a moment. So what? Like I'm sure that look. In physics, typically for response functions, what we have is we have simple poles like this. Simple poles like this are like sharp excitation. Or you have branch cuts, which are like a continuum.
Right.
So for branch cuts, it also we can actually.
No, I don't think you can have branch cut because branch cut is like infinite, so this won't be 0.
No, you don't have to have an infinite. You can have a branch cut between 2 points.
Okay.
It doesn't have to be.
So you can have like opposite branch cuts, I guess. Can you?
But I think that any branch cut that would end at a point would contribute also some oscillatory part. Like it would get some.
Yeah, I think this is like the main idea in the Jordan level.
Okay. So you guys are convinced.
Yes.
Good.
But it's easy to fool us.
What? It's easy to fool you?
Yes.
No, I don't think so.
I would say that if to not be convinced will waste our time. So
no, but I guess yeah, that's something I also forgot to mention. I think today's class is going to be shorter. I also need to write an exercise. I remember that. I'm just way behind on everything. Okay, so now what I want to do is I want to take advantage of the fact that chi is analytic in the upper half plane. I want to take advantage of that to get some relation between its real and imaginary parts, which is known as the Kramer-Kronig relation. So to do that, I first want to define, okay, so we have a small detour, okay, I'm just going to discuss, analytic functions in general. So let's assume that rho of omega is rho of z, let's call it rho of z, is an analytic function. Okay? Then we can define the function f of omega is equal to 1 over I pi, the integral from minus infinity to infinity, rho of omega prime divided by omega minus omega prime d omega prime. Now this integral obviously has a problem because it has this divergence when omega is equal to omega prime, which makes it not well defined. Okay. But if we displace the pole slightly above or slightly below the complex into the complex plane, then this integral becomes well behaved, and we can use that. And the idea would be to say that if I take f of omega plus I epsilon minus f of omega minus I epsilon, then I just get rho of omega. And if I look at 1/2 f of omega plus I epsilon plus f of omega of minus I epsilon, then I get 1 over I pi, the principal value of the integral from minus infinity to infinity, rho of omega prime divided by omega minus omega prime d omega prime. And here I'm using the relation that 1 over x plus minus I epsilon, in the limit where epsilon is going to 0, gives us the principal value of 1 over x minus plus I pi delta of x. Okay? Which is also attributed to Dirac, as far as I know. And the principal value, in this case, the principal value, of this integral from minus infinity to infinity, rho of omega prime minus omega, I think I made a mistake here, is like writing an integral from 0 to infinity, rho of omega prime minus omega minus rho of omega, omega. Yeah, now I understand what I wrote. Okay. Omega minus omega prime minus omega the omega prime. What this implies is that the principal value is a principal value around the pole. Okay, so basically we're taking the contributions on both sides of the poles with equal weight. Okay. Good. So what I'm really going to need is this equation. Star. And this equation. No operators. So P is the principal value. So when you see the problem with these kind of integrals, if you think about 1 over x as a function that you're integrating over, right? The integral from minus infinity to infinity dx over x. Okay, it could be anything because no, not necessarily, right? Because it depends on how you take your limits.
Yes.
It's antisymmetric, so naively you could say it's 0, but it also diverges. So this is so the principal value is a specific definition, and if you write the principal value of this, then it is 0. It means that I'm taking the two sides of the integral symmetrically, and then I'm taking the integral to infinity. Okay? For example, this is known as a principal value. So now
principal value without an integral.
it's like a delta function. By the way, what's a delta function without an integral?
So you take
exactly. Okay. Now, okay. So now let's use this analogy to, we know we have this function chi, which is analytic in the upper half plane. So I'm going to plug it in for this rho. So I'm going to define f of omega is equal to 1 over I pi a closed contour which goes in the upper half plane dz chi of z divided by z minus omega. Okay? And therefore we can use these two relations to say that chi of omega is equal to 1/2 f of omega plus I epsilon minus f of omega minus I epsilon. And epsilon is, I didn't mention of course, but, and 1 over I pi, the principal value of the integral from minus infinity to infinity, d omega prime, chi of omega prime minus omega, is equal to 1/2 f of omega plus I epsilon plus f of omega minus I epsilon. Okay. Now, so that's the first thing. Now we can take the difference between these two equations, and therefore we get that f of omega minus I epsilon is equal to 1 over I pi, the principal value from minus infinity to infinity, d omega prime, chi of omega prime, omega minus omega minus chi of omega. Okay? But on the other hand, what?
Instead of adding them, you can subtract them. So subtracting them, you can add them. This is what you meant to do?
No, it's not what I meant to do. What I meant to do, but now suddenly seems a bit odd to me, was to argue that because of the properties of chi, which is analytic, then this thing is 0. But maybe it's actually, let's see if that's true.
I think the integral is not like the borders. It's supposed to be half circle. Right? It's not supposed to be from minus infinity to infinity because we defined it.
Where? Here?
Yes.
No, but this is the
Really?
principal value. This is something else.
But you started with a different integral than what you did before.
This.
Yes.
Ah, you're saying that here it should be.
Okay, that's one option.
So if I take. So. Wait a second. Okay. But chi is analytic. However, because omega minus I epsilon. Oh, I see. Yeah. So okay. So the point is this. The point is this: that if I plug this, right? F this guy is also like an integral 1 over I pi, right? An integral from minus infinity to infinity, d omega prime, chi of omega prime minus, let me call it z naught, okay? And this z naught is going to be exactly omega minus I epsilon, right?
Yes.
So that means that I have, omega here. Here I have the imaginary part of z. Then z naught is somewhere here. Let's call this omega prime. Okay? This is what I'm doing the integral of.
Okay.
So it means that the pole is shifted downwards. Okay? So if I want to do this integral,
Okay.
right? So I can just close the integral here because I know that chi is analytic. Okay?
Okay.
And this will cause a decay. So because I know this doesn't give me any poles inside there. And this also doesn't give me any poles inside. So this thing is equal to 0. So that's the claim. Okay?
Why does it?
The integral, right? Gives you 0.
Okay. Okay.
This thing is an integral.
Ah, right. Okay.
But it's an integral where I shifted slightly below.
Okay.
Right. But when you integrate on the upper half contour,
Yes.
like it decreases, but
What decreases?
the integral.
No, but I'm taking but this is
Um,
I'm taking it to infinity.
Yeah, but I'm not sure it decreases fast enough.
Ah.
Yeah, that's.
But okay, so if chi is exactly constant everywhere,
Yes.
right? It's just a constant.
Yeah.
Okay? Then you're right. Anything that decays faster than that, I'm fine.
Okay. So
You agree?
Yes. Yes.
Okay. Now, if chi is a non-trivial analytic function, then I argue, okay, let's see. First of all, if chi would be just a constant everywhere, that would be a very sick response function. And you could ask if it is analytic. It's
Like it's when you mean constant in frequency space.
yes.
So it's still sick to be constant.
What?
Is it still sick to be constant in space?
But also, you can relate that to the derivative. If it's constant, it would be 0. So each integral, you can, by Cauchy theorem, relate it to a derivative, right? So an integral would be 0.
you're saying if chi of omega, you see, you guys promise to be nice and you're not nice. So if it's just a constant, you're saying that that still this thing can you can still prove that it's zero.
It would be this would be exactly a constant, and I don't know if it would be if you would have any meaning there, because
No, I don't think.
like
I don't
rho would be zero,
What?
zero, because if f is a
Well,
constant,
if
rho would be zero.
Yes, rho. If f would be constant, no, but we're not talking about f. We're talking about chi.
you can. Like
So what Zvi is proposing is that when when you use these kind of arguments, you need to make sure, right? We're changing the variable z to be some r e to the I theta, right? And we need and then when you do the integral becomes dr r, right? 1 over r e to the I theta. And then this r and this r, they cancel.
Right. Yeah.
Okay, so it means that the denominator needs to decay faster than 1 over x. Okay, and therefore Zvi is asking, what about the constant response? So a constant response is indeed a delta function in time. Hey, what is a delta function in time? So delta function in time.
I think if it's just a constant, then the argument is still valid. You can just move psi outside the integral.
Psi?
It will give you 1.
Yes.
And it's okay. Psi is equal to psi. I mean, the claim that this whole thing is equal to 0, it's valid that psi is a constant by, I can calculate it.
Yeah, but
Then it's okay. It's like
you're saying this integral will just give me half the e to the I pi, which would give me pi.
Yes.
Yes. Exactly. I mean, להפריד למקרים כאילו.
Okay. So in this specific case, even this sick limit works. Okay, good. That's how I like you, much better when you answer your own question. Okay, good. So basically, what we got, okay, let me summarize. Because chi of omega is analytic in the upper half plane, and we saw this cute relationship between analytic functions, we found that chi of omega is actually related to itself in some funny way, 1 over I pi, the integral from minus infinity to infinity, the principal value. Okay. Now we can further define chi of omega as chi prime of omega plus I chi double prime of omega. Okay? And therefore we get a very interesting relationship, which is basically the Kramer-Kronig relations, that the real part of chi, because of this 1 over I here, is going to be 1 over pi, the principal value of d omega prime, chi double prime of omega, omega prime minus omega, and chi double prime of omega is equal to 1 over pi principal value from minus infinity to infinity d omega prime okay, so this, first of all, this relationship by itself is very powerful because it means that if you know the imaginary part, if you know the entire imaginary part of chi, then you also know the real part of chi, and vice versa. Okay, and that's very important in spectroscopy for experimentalists, because many times they can only measure one side. Okay, they have another problem, that their frequency range is never infinite. So in order to convert from one to the other, you need the entire range. So that's a bit of a problem. But at least if they assume that they have the major part and so on and so forth, neglecting these inaccuracies, they basically can have the entire response function by just measuring, for example, absorption, okay, or dissipation, and not only the response, or vice versa. Okay, now I want to take advantage of this guy, okay, this equation, to write another version of the Kramer-Kronig relation, because remember that in our case this guy is 0, right? So what I want to say, what do I want to say? It's a good question, what I wanted to say. Yeah, I wanted to say that the chi of omega what did I want to call that? One moment. I know. Hold on. So there's another way of writing relations. Okay, so let me define a function similar to this f, okay, which I will call g of omega, which is going to be 1 over I pi, the integral from minus infinity to infinity, d omega prime over I pi, chi double prime of omega divided by omega prime minus omega. Okay? Now, according to what we've just shown, then g of omega plus I epsilon wait a second. Okay, this guy, okay, so imagine that I take these two equations and I sum them up. Like you said before, I can sum them up. So then I can extract this guy. And then on this side I get chi double prime. And here I get this principal value integral. So I get that this is equal to chi double prime of omega, now plus this 1 over I pi, the principal value of chi double prime of omega divided by omega minus omega prime, right? Good. So, but we just got from the Kramer-Kronig relation that this guy right? Is just
Right. This is true for only one I pi, right?
What?
רק כתבת G שווה ל-1 חלק ל-I pi ועוד פעם 1 חלק ל-I pi. זה בכוונה טעות זאת שיש.
where?
זה
זה
I
טעות,
pi?
זה טעות, זה טעות.
אוקיי.
אגב, גם שם יש, there is a minus there.
Where?
In the relation.
Right. So this chi double prime of omega is minus, right?
Yeah.
Good, thanks. Yes. This is this is because here if I plug in the real part, then this is 1 over I. Gives me a minus. Yeah. Thanks. Okay, good. So this thing is what does this give me? This gives me chi prime of omega divided by I. Right? So it means that this whole thing here is like chi of omega divided by I. So what we get is that G of omega plus I epsilon I is chi of omega. So now do you see that chi double prime is the imaginary part of the response function? Do you see it already?
Just multiplied by I.
No, that's not the point. The point is that if I put, now let me sum this up, so I get that chi of omega, okay, is 1 over pi, the integral from minus infinity to infinity, d omega prime, chi double prime of omega, omega prime minus omega minus I epsilon. Okay, now sorry. This chi double prime, that's not what I meant. I said it wrong. This chi double prime is without a doubt the imaginary part of chi. That's how I defined it here on the board. What I meant is, now you can see that this chi double prime is the chi double prime that we defined. Let me write it again for you, and then you can see it for your own eyes.
With the theta function.
Yes, exactly.
Yeah.
With the theta function. So we had that chi of x and t is equal to 2 times I theta of t, right? Chi double prime of x and t. Or let's forget about x. T. X doesn't matter. Right? Because what is this? It's a convolution.
Right.
And what is the Fourier transform of
The
the
product
theta function? It's this guy. Okay?
Right, yeah.
Good. So now we've closed the loop. We've proven that this chi double prime, which we found is responsible for the dissipation, is actually the imaginary part of the response function. And also we found 2 different ways that you can imagine to obtain both parts or the entire the entire response function just from one of the parts, for example, the dissipative part. This is known as Kramer-Kronig relation. Okay, and I think now is a good time to go for a break. Then we'll have another short session, and I'll let you guys go with a bit less this time. But Tzvi, you might be happy that today is the last day of linear response theory. Okay, that's it. Today we finish with linear response theory, and next lecture will be RG. Okay, and in the exercise, I need to write an exercise. I'll give you to compute the response function, okay, using field theoretic tools. So sorry. V spectrum. Okay, so let's assume by what wizardy we somehow diagonalized the time-independent part of the Hamiltonian, so we have a spectrum. Okay. Now let's look at our definition for chi double prime. T. I wonder if I need this ij. For some reason, I generalized at this point the susceptibility to a vector field instead of a scalar field. I'm not confident enough to throw that away. Let's call it alpha beta. Okay. But maybe it's not that important. The point is that you could imagine that you couple the vector field instead of a scalar. So we've defined this to be the expectation value. Sorry, 1/2 the expectation value of phi hat alpha of t phi hat beta of 0. And now let's assume that this expectation value here is an expectation value over a thermal state. So we're computing this in a thermal state. So we get 1 over z, the trace of e to the minus beta h 0, e to the I h 0 t phi alpha Okay, using this spectrum, we can rewrite this as 1 over z sum over n e to the minus beta h I t plus I beta h naught
You have like
okay. You know what? Let me know. What?
you have several fields.
You're asking what this alpha beta is?
Yeah.
So it's just okay. For whatever reason, at this point in my notes, I generalized susceptibility. Maybe it's a good point to mention that you could also couple to a vector field instead of. So imagine that you have multiple fields and they're like a vector, and then the susceptibility, for example, could be a tensor instead of a scale. But nothing really changes. I don't remember. The problem is I don't really remember if it has some crucial implications. So I don't want to erase it now and then regret later on doing that. Maybe that's right, like this. Then we have phi beta n minus sum over n e to the minus beta h naught phi beta e to the I h naught t phi alpha e to the minus I h naught t. Now what I'm going to do is I'm going to insert a complete set of states. Let me denote this in red. I still have my red. So I'm going to flag this complete set of states. Here I'm going to put it here. Here, I'm going to put it here. Okay. Now the point is that by doing this, I can act with these e's. So here, this guy, for example, right? This guy gives me e to the minus en t. Right?
Yes.
Right.
Yes.
And these guys here will give me the same thing. So this part, for example, will give me e to the minus beta en e to the I en t, for example. Okay? So with these m's now, I can also act with the internal h's, and I end up with just matrix elements. So I have 1 over z, sum over n and m, which are the energy states, e to the minus beta en. Then I have phi alpha nm, phi beta nm, which are the matrix elements of these fields. And then we have, e to the I en minus em t minus phi n m alpha This is M N. I chose very non-confusing indices. So now it's the other way around. It's beta first. And then here it's phi m n alpha, and then e to the I e n minus e n t. Okay. Okay, so this is a chi double prime of t, and from this I conclude that chi double prime of omega, this dissipative part, say alpha beta in this case, is 1 over z sum over n and m. So I just Fourier transform this, and these guys give me delta functions, right? So I get 2 pi e to the minus beta n. Then I have this phi alpha. I don't see actually what's the big deal here, but delta omega minus en plus en minus phi beta and m phi alpha and m delta of omega minus em plus en. Okay, and what's nice about this expression is that you now get another intuitive point of view on this dissipative part of the response function, because you can see that it's basically a so these are matrix elements, okay? But these guys, they tell us about the absorption at the many-body energies, okay? So n is like the it's the response function. Okay, maybe a good way to think about it. Let me see if we've already discussed this. I remember discussing it in one of the courses I taught, but I don't remember which. But the point is that this, you know, like in the Fermi golden rule, you kind of think about, so the imaginary part of the response function can be thought of as a kind of Fermi golden rule, and then we can think about these m states as some intermediate state. Now, what am I trying to say? What I'm trying to say is that there is an absorption term and an emission term, right? Because this is like the energy of the initial state minus the energy of the final state, and here it's reversed. So there are processes, there are intermediate processes in which, you know, there is emission into the medium and absorption into the medium. And this is what these two terms represent. So that's another kind of powerful intuition about what this dissipative part of the... Now we can further take advantage of what we've just derived, the Kramer-Kronig gradation.
Yeah.
Yes?
Can I ask, I think in a way it's basic, but it seems like you have a field here, but you also have states, like all quantum states in the same. So, like, how can you?
You're asking. I think what you're asking is if these are fields, then what are these states? That's your question?
Yes.
So I want to remind you that, first of all, in our first exercise, I think I gave you to derive the wave functions of these states. So for these fields. So the fact that we have a field and it's not, it's no longer wave functions, say, of a single particle in some well-defined coordinate space, but now we've generalized this such that the coordinate is the magnitude of the field, and the coordinate in space is just an index for many of these fields. You can still write a wave function, and these wave functions will still have energy. So this relationship still holds. Okay, so the Hamiltonian has a well-defined spectrum. Now it could be that the spectrum is continuous or discrete, but still there is such a spectrum. And that's actually all I really need to know, because within this spectrum you have to agree with me that these fields have some expectation value in the eigenstates of the Hamiltonian. Okay, and how to compute that, that's a question. Okay, and we'll get to that later on within field theory, for example. But actually, you know how to compute these kind of things, because you can use Feynman diagrams, for example, and path integrals to compute such expectation values. Okay, and that's these matrix elements that you see here, and these energies are energies of the many-body Hamiltonian, which that can be challenging. But let's see where we can go with this. Okay. But so what I wanted to do is I wanted to use this Kramer-Kronig relation. In particular, I erased exactly the Kramer-Kronig relation I wanted, which is, maybe I'll write it again here. We said that chi of omega is equal to 1 over pi, right, the integral d omega prime of chi double prime of omega prime divided by omega minus omega prime. What was it? Minus I epsilon or something, right? I hope I got the signs right.
נראה לי הפוך, זה אומגה פריים פחות אומגה. אם העתקתי נכון.
No, I think you're right. Okay, so if we plug this in here, you see that chi double prime of omega is a bunch of delta functions. So it's a very fun integral to do. Right? So we get that chi alpha beta of omega is just 1 over z, sum over nm, e minus beta en. Then we have this phi nm alpha, phi beta divided by en minus em so let's see, so we have that, so omega is that, then we have minus omega minus I epsilon minus phi alpha, phi beta So what you see here is that the response function is just a bunch of poles at the many body energies, okay, which are shifted slightly below. So, you know, the energies are real, right?
This is some sort of 2-point correlation function.
It is for sure a 2-point correlation function. Well, that's what we've been discussing for the last. Yeah.
Yes. Here, like you can see it exactly.
Well, we also saw it before because you see these, for example, this chi double prime was this, and the way we got it was from linearizing the response. But what I wanted to mention is that, you know, these energies are real because the Hamiltonian is Hermitian. So this sum over here, basically, you know, especially if you take temperature to 0, you can see that, you know, if I look in imaginary of Z, and this is a real of Z, which I call it omega, then I just have a bunch of poles that are, you know, slightly shifted below, such that the response function would be causal. Okay, but you could imagine that if the system is finite, you have a finite number of degrees of freedom, then these spectrum will be discrete. But in the thermodynamic limit, right, you're just going to have a branch cut. Okay, maybe I should draw it like, which is sitting slightly below. Okay, so that's one thing to mention. And another thing to mention is that it looks, if you look at this expression, it looks like, you know, once we have this branch cut business, it looks like this response function is not only analytic in the upper half plane, it's actually analytic everywhere except for this branch cut. Okay, that's what seems to be implied by this expression. So it's analytic above the branch cut and analytic below the branch cut. But we just have a relationship, right, that if we write the limit of chi of omega minus I epsilon, epsilon goes to 0, is not equal to the limit of chi of omega plus I epsilon. Okay, and yeah, and this guy is known as the retarded response function. And this guy is known as the advanced. Okay. Now to the main, like the ultimate goal of this whole discussion, I want to discuss the relation between real and imaginary response function. So consider, instead of this perturbation we had before, imagine that our action is now some action. So we're thinking now about a thermal what's the name, partition function, using using path integral formalism to compute the partition function, the quantum partition function. And imagine that to this partition function we add a field that depends on imaginary time. This is of course this has no meaning. Okay, you can't do something like this. But let's imagine for a moment that we do that. Then we can write that we can define an imaginary time response function, which I will denote as chi m. Okay, this thing is equal to 1 over z of 0. Okay, sorry. Before we do that, let me denote it like this. And then S naught is some action. Then we can define chi m of tau minus tau prime as 1 over z naught delta squared z of f divided by delta f of tau delta f of tau prime at f equal to 0, and this just gives us the expectation value. This is basically the Green's function, right? This is nothing but the Green's function. It's basically phi of tau prime. Okay, we've seen that.
Something very similar was in the homework.
Yeah, it was completely planned. Okay. So now let's write this guy in the spectral representation. So I want to argue and did we ever discuss this
Time
ordering business?
Not really.
No, we saw causality with your
No. Time ordering is not causality.
No, time ordering operator.
It's a different.
We mentioned it by the side.
No, we did not. We did not discuss that.
No, we did discuss the time ordering when we discussed the evolution of it.
Yes.
But okay, but the point is this. The point is, what you see here is okay. You could ask. Okay, so this thing, I'll have to show it later. But basically, when you take these kind of derivatives, okay, you always get the time ordered. This is a general, by the way. It has nothing to do with imaginary time. always when you write a partition, when you do a path integral, okay, and you couple your field, your field to some external source field in order to compute the correlation function, the correlation function that you get is going to be the time ordered correlation function. Okay, and I'll have to show you that later. Okay, so this is a kochavit. Okay, but assuming you have this, okay, assuming that I showed you this, then chi m alpha beta of tau is 1 over z of 0 sum over L and M e to the minus beta EL sum over L e to the minus h tau phi alpha e to the h tau phi beta L theta tau plus this is the, so time ordering just means that, you know, if there if tau is if tau minus tau, you know, okay. Oh my god, okay, this is not tau. Let's write this minus h tau minus tau prime, and this is h tau minus tau prime. Okay, so what this means is that when tau is larger than tau prime, then they come in this order, and when tau is smaller than tau prime, they come in the opposite order.
So
Okay.
inside the theta function you have also tau.
What?
Inside the theta function you have
Yeah.
also.
Yes,
Right.
yes,
Okay.
yes.
Okay. Okay. Okay.
This is okay, and then I have maybe I can write it like this. Then I have
Isn't it the same calculation as before?
it is same. I don't know about the same calculation, but it is very similar indeed. One moment. Phi beta m e to the minus h tau. I see that in my notes I have a lot of mistakes, but this is not I. This is h tau L theta of tau minus tau. Okay, and you guys will help me spot the mistakes. Okay, that's why you are here.
The exponent it's like tau.
It's what?
It's tau alone or tau minus
It's tau minus tau.
Okay.
Yeah, I should have just given it a name. Right. I'm basically assuming time invariance. then this is equal to 1 over z sum over Lm e to the minus beta El e to the minus El minus Em tau phi Lm alpha phi Ml beta theta of tau minus tau prime. This is again tau minus tau prime. And then I have plus, okay, maybe I'll just write it like this, then I have plus, okay, okay, my bad.
Shouldn't you have the tau and tau tag switch in the second expression?
Which second expression? This?
Yeah, I guess like what you mean is when tau tag is greater than tau.
Ah, this is tau.
Yes.
Tau.
And probably in all, also in the exponents, right? Or
Yeah. No. Why? No. This I don't think so. No.
why not? But
Because okay, I'll tell you what. Because here, okay, here I'm invoking the fact. Okay, I'm claiming that this expectation value. Okay, I should have been more explicit. But the first thing I want to claim is that due to time invariance, this is equal to tau of phi of tau minus tau prime, phi of 0. Okay, that's the first thing.
if you assume tau is greater than tau 0.
No, it has nothing to do. The
Okay,
time
this-
ordering will take care of that.
Yeah, this is invariant of time.
Okay. And then this thing is equal to phi of tau minus tau prime, phi of 0, times theta of tau minus tau prime, okay, plus phi of 0, phi of tau minus tau
Okay.
prime, theta of tau prime minus tau.
Oh,
Okay. Sorry for all that mess. This guy is 1 over z. Sum over So here I've cheated. I didn't cheat, but I switched the roles of L and M such that this looks exactly like this looks exactly like this. What? Ah, beta. And I've made beta equal to 1 in this term. Z, I don't even remember. So I get e to the minus beta El theta of tau minus tau prime plus e to the minus beta M theta of tau prime minus tau, and then this whole thing is equal to phi Lm alpha phi ml times e to the minus el minus em tau minus tau prime. Okay. Now, okay, what do I want to say? Now, another point is that I want to remind you that all these fields, phi of tau, are periodic with tau going to tau plus beta. And because of this invariance I wrote here, this also holds to tau minus tau prime. Okay, so if I shift this parameter tau minus tau prime, in fact, let me find a new name for tau minus tau prime, because if I won't, I will start to get confused. So let me denote this by, let's call it, say, gamma. So gamma is equal to tau minus tau prime, just so I won't get confused with my notes. Okay? And therefore this whole response function is a function of gamma and is periodic in gamma going to gamma plus beta. Okay? And that implies that I can write chi m of I omega n Matsubara frequencies alpha beta is equal to an integral from 0 to beta d tau chi m alpha beta of tau e to the I omega n tau. Okay, because this is inherently periodic.
Why is periodic?
You're asking why does this imply that it's periodic, or why in the beginning I implied that it's periodic?
Yes.
Because this whole formalism is taken from this path integral formalism, which is it's basically a way to compute partition functions. Now I remind you that the way we did it was that we started from a trace over e to the minus beta h, okay, and then we wrote this as a sum over n e to the minus beta h n, and then we opened it up into very small increments. Blah 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 blah. We got some path integral of
you're talking about coherent states.
What? Coherent states, exactly, a coherent state path integral, where the fact that this is a trace means that we begin and end at the same point.
Yes.
Okay.
Okay.
So that means that this thing is periodic. Now, a pokey question you could have asked is what happens if these are fermions? If these are fermions, so then you can ask about this field that we coupled. Okay? But as you will see, first of all, I want to comment that we don't have probes that couple to a single fermion. If you have one, let me know. You can make millions, but you don't. Okay, so it always is some fermionic bilinear. So that implies that whatever you couple to it might be a composite of fermions, but effectively it's a bosonic field. Okay, so that means that it's periodic and not anti-periodic. But even if you would couple to fermions, the response function would still be in bosonic Matsubara frequencies, because it is a function of pair of fermionic. So now we can explicitly calculate this thing. And what I claim is that we get 1 over z sum over Lm. Okay, here. Yes. So we can compute this integral exactly, right? Because we have, gamma. Okay, that gamma over there. Okay, so if we do this calculation, we get 1 over z phi alpha Lm phi ml beta divided by I omega n minus El minus Em, and then we have e to the minus beta En minus e to the minus beta En. Okay? Now we can compare this result to, I erased that result. Okay, so let me rewrite the result we had before. So before we had chi alpha beta of omega was 1 over z sum over nm e to the minus beta en, and then we had phi n m phi m n alpha beta e n minus m minus omega minus I epsilon minus phi alpha phi beta phi alpha n m m n e m minus e n minus omega minus I epsilon. Okay, so now I want to compare these two expressions. So what I can do is I can switch what I call n and what I call m. And these two expressions, this thing is equal to 1 over z sum over nm. I don't know why I did it so cumbersome, but this is basically phi nm alpha phi m n beta divided by e n minus e m minus omega minus I epsilon times e to the minus beta e n plus e to the minus beta e m. Okay? So if I compare these two expressions up to n and L, this is a minus. Where did I get this minus from? I don't remember. Minus. This is minus. No, this is, the point is that this is theta of gamma and this is theta of minus gamma. So I think that's that's the point. Okay, we can check that in a moment, but if you believe me,
How can you really compare those expressions? Because on this expression you have like Matsuba frequency, which is discrete, and here you have continuous.
Because it's the analytic continuation.
No, that's okay.
no, I'm not comparing. That's exactly the point.
Okay.
I do have a problem that they're not exactly the same because of some minus sign. Okay, I was probably a bit sloppy here with the minus sign, but you guys will, you get the message, okay? Let's not be aggressive towards me regarding minus signs.
Well, what's the point of the minus sign? Like
No, the problem is that this, okay, you'll see in a moment. I'll first make the statement and then you can argue about the minus sign.
I think I know when we got this minus.
Well, what is, okay.
Bit like in the beginning of the lecture when you related chi prime prime. Like in last lecture you had a minus sign between the relation, and this lecture you didn't have a minus sign. So I think the minus sign is from there. I thought to myself that it doesn't matter because when you measure it, you know, like you don't care about the minus sign. But,
Okay, so you're willing to accept that here there is just a magical minus sign.
Yeah.
Or on the yeah.
Woo! Thanks. Okay. Saved by the tzvi again. Okay. So now, okay. What's the big point here to be made? The big point to be made is that we find that these two expressions are actually identical under the substitution. So, okay, so let me try and make a connection between these two. So the claim is that this guy has, you know, this branch cut is sitting on the, so okay, you know what, let me try and explain what I want to do. So imagine that I look at two functions which I analytically continue into the complex plane. Okay? These are my two functions. Okay? Both of them I analytically continue them. How do they compare one with the other? So if I just instead of this I omega I put a z there. Sorry, if instead of, oh, sorry, no, that's not what I mean. I probably mean IZ. IZ, because I already wrote the I here. It's very confusing, these notations, because if you write I omega, it's like already making the substitution. But assume that I take this function, and instead of omega, I write Z. If one more person opens that door, I'm going to shoot you. Okay. If I put a Z there, then you see that the entire spectrum that I had here, so let's assume that that branch cut I was talking about before is here, slightly below this axis. Then now I have it here on this imaginary axis. Okay, so that's basically what we're seeing. So the two can be related by this kind of wick rotation. So from here, we conclude very valuable relationship. Yes, okay. That chi of omega is equal to chi m of omega plus I epsilon. Okay, so if you compute in Matsubara space a function of I omega, you can just analytically continue it to get the response function. This is the key result. This is what I wanted to prove. I don't know if I did a very good job, but this is a very, I don't want, whether I was a bit scattered with everything, I don't want it to ruin the importance of this result. What this result tells you is that you can use all this path integral formalism that we wanted to compute response function in this insane imaginary time that has no meaning whatsoever, and then use that response function, its frequency, its Matsubara dependence, to obtain the actual Fourier transform of the real time response function. Okay, at thermal equilibrium. So notice that we've assumed here thermal equilibrium, and that's very, very important. Because if we wouldn't assume thermal equilibrium, then this whole thing doesn't work. This connection only exists at equilibrium.
Yeah.
Okay.
Oh, why you don't have an I there?
Here.
Yeah, exactly.
Because I defined this with an I. That's what I was saying. It's a very confusing notation. But you see, this is like a function of I omega.
Yes.
Okay? Now, why am I writing it this way? Because that's how it's conventionally written. It's kind of like the analytic continuation is already done.
Okay.
It's just a stupid definition. If you like, we could go back and define this. Yeah, we could just erase this I here.
Yes.
And then leave everything the same. Okay. And then it would be like so we want to put I omega. So we write here I omega minus epsilon.
Oh.
Is that good?
Yeah.
Plus epsilon. Plus.
Yeah,
No, minus.
And then what's the
what?
significance again? Like you define it on Matsubara frequencies, and then you're like.
What's the significance? The significance is the following one. Calculating response functions in real time, okay, means that you need to calculate all these Green's functions where they have poles. Okay? You have to imagine, for example, that this response function. So this response function, okay, I wrote it here as a spectral function, but you don't have to compute it like that. Look at it here. It's just a correlation function between two fields. So, for example, let's look at an example. Okay, let's try to. I don't have my notes here, but I'll try to remember.
Yeah, I have your notes.
What?
I have your notes.
Good. You have mine. So let's imagine, for example, that you have a field. Okay. So V of t is some integral over space mu of x and t psi dagger, or maybe even I'll write c dagger of x, c dagger of x. So these are fermions, and you have some something that couples to density. For example, this mu of x and t could be a squared of x and t, which is, you know, imagine that I write something like minus I grad minus EA psi, you know, squared over 2m. Sorry, and this term has the expression where a squared couples to psi. Okay, so this term is like it's like a vertex that looks like this. Okay, and for example, one gets this is if you want to calculate the fermionic response to a Raman experiment where you have a photon in, photon out. So overall you don't have. This term contributes significantly. So that's why Raman experiments, they're very good at probing density. Okay? Because you see it's coupling to density. So let's say you want to compute the response to this thing. Okay? Now you could try and calculate the real-time response function. Okay? You could try to calculate, you know, okay, so you could say, okay, I want to calculate then, therefore, you know, C dagger of x and t, C of x and t, you know, C of x prime and t prime, dagger C of x prime and t prime. Okay? And then I could open this thing, okay, and this is the whole, so I need to take all the, and then I need to compute them in real time. And Green's functions in real time, in real frequency, they have poles, and it's a whole mess, okay? But it turns out that this calculation is much easier to do in imaginary time. So first of all, in imaginary time, I don't need to compute this commutator. And the second thing, and this is more important, is that these calculations, they don't have these poles. They don't have these divergences. So it's much easier. I'll talk to you in Peskinit. In Peskin, when you read Peskin's book, you go over it, you'll see that many times when he computes bubble diagrams, for example, he does a Wick rotation, right? Did you notice that he does this Wick rotation? He moves to Euclidean time instead of real time. Why does he do this Euclidean time calculation? Why? Why not do it in real time?
It's just easier to solve this integral.
Exactly. So same thing is here. It's much easier to compute these correlation functions in Matsubara space. And in Matsubara space, you know, chi m of this field mu, let me call it mu, of I omega and q, you know what it is? It's basically this guy. Right? Where this is k and omega, and this is k minus q, and omega, not omega, let me call it mu, and this is mu minus omega.
So it's like the imaginary part of the self-energy, it's the first thing that we saw in the lecture today. I think there's a way to relate that.
One moment. It's this. Okay, I'm gonna shoot him.
You still
אפשר אולי לשאול אותם מה יש להם, מה האינטרס שלהם להיכנס לפה.
I don't know. But, okay, יש תרגול. אבל יש תרגול, בואו תיכנסו, יש תרגול, בואו נעשה. אתם רואים? זה התרגול. So you remember we calculated this. Okay? That's it. We have the response function. Okay? We know how a Fermi gas, for example, Fermi liquid, would respond to Raman fields. Okay? All we really need to do is to analytically continue this expression to a real frequency. And it's that easy. All we really need to do is do this substitution. Okay? So it's super easy.
And we know that the susceptibility equals to this bubble because of the correlation function.
Because we calculated it.
But we know it's the correlation function, right? Between I'm asking.
Yes, exactly. Because chi m, maybe it's erased, but chi m. I want to remind you that chi m of omega is the Matsubara version of the imaginary time correlation function tau, right? Which is the time ordered phi of tau, phi of 0.
Okay.
Okay, and this we know how to calculate.
Yes, it's basically.
So when someone comes to a seminar and says, "I calculated the imaginary part of the self-energy," they mean this in the experiment?
Specifically, the imaginary part of the self-energy. The imaginary part of the self-energy is the damping. Okay, that's general. Because okay, what is a self-energy? A self-energy, when we say self-energy, what we really mean, and we've seen this, right? We've seen this. That so it depends on if it's a bosonic or a fermionic field, but a self-energy means that it typically implies an equation like this. Okay, where this is the self-energy,
right?
This is the bare Green's function, and this is the renormalized Green's function,
right?
Okay, so that implies that your Green's function has the structure of g naught to the minus sigma, and therefore the imaginary part of sigma, assuming that these are sharp excitations, the imaginary part of sigma is the damping of these excitations.
Okay.
Mm-hmm. So when people say that they compute the imaginary part of sigma, they mean in real time. Now, many times, for example, if I want to compute sigma using Eliashberg theory, okay, it's going to be much, much easier, orders of magnitude easier, to compute sigma in Matsubara space and then analytically continue it, instead of to try and calculate it in real frequency to begin with.
Okay.
Okay? So the last thing I wanted to say, what's the time, by the way? It's late. Okay, I think I can just levater on this part. And what I really need to do is write an exercise. And I know I've been neglecting that, but I will do that. I will do that. Okay? Mm-hmm.
יש לי שאלה שראינו בהרצאה.
כן.
כאילו, יכול להיות שספק. אתה אמרת שאם הטמפרטורה צונחת לאפס, אז זה יהיה ברנצ'קט, נכון?
לא, אני חושב שזה ברנצ'קט. בוא נראה. אם הטמפרטורה צונחת לאפס, אז זה בטוח ברנצ'קאט. מה קורה כשהטמפרטורה לא אפס?
למה זה בטוח ברנצ'קאט? כאילו זה תלוי בהפרשים בין האנרגיות, לא?
לא, אבל אוקיי, אז פה יש טענה אחרת, שהאנרגיות הן דיסקרטיות, כאילו יש שם סכום על המצבים והאנרגיות שלהם. האנרגיות הן דיסקרטיות במערכת סופית. במערכת אין סופית, בדרך כלל שאנחנו לוקחים את המערכת הגבול התרמודינמי, אתה לא חייב שיהיה לך רצף. כלומר, יכולים להיות אזורים בדידים בספקטרום, זה מאוד מיוחד דרך אגב כשזה קורה, אבל באופן גנרי אתה מקבל תחומים מסוימים שיש בהם קונטיניום.
אוקיי, זה ברנצ'קאט.
ואז זה הופך להיות ברנצ'קאט.
ולמה צריך שהטמפרטורה תהיה אפס?
למה צריך שהטמפרטורה תהיה אפס? אני לא בטוח שאני צריך שהטמפרטורה תהיה אפס. זאת באמת שאלה, כי אם הטמפרטורה היא לא אפס, אז הדבר הזה הופך להיות אינטגרל. אתה צודק, זה עדיין כנראה ברנצ'קאט. כלומר, אני חושב על זה בתור פולס, ואז שעושה אינטגרל על פולס, נכון? אם אתה לוקח פולס להיות רצף ועושה עליהם אינטגרל, אתה מקבל ברנצ'קאט. זה פשוט לוג פשוט. אבל ברגע שיש כאן את התלות הזאתי, אז זה לא בדיוק הלוג הזה, זה...
מה שפריע לי שכאילו האקספוננטים מתבטלים קצת, לא?
זה לא שהם מתבטלים...
שמתבטלים יותר...
מתבטלים...
אולי מתבטלים יותר איטי מאשר
אתה שואל...
אולי מתבטלים יותר איטי מאשר...
אתה שואל מה קורה כשאני לוקח את זה לאפס וזה 1 פחות 1, כאילו.
כן. יכול להיות שפשוט זה 0 יותר מהר מאשר 1 פחות 1.
כן. כמובן, זה לא מתאפס. הגבול נשאר סופי, כן. חייב, אחרת אין רספונס באותו האפס.
או שעשינו שטויות.
זה יכול להיות, זה יכול להיות. בוא נסתכל רגע, נראה אם אני העתקתי פה משהו לא נכון רגע. לא, אבל אני אגיד לך מה. כן. תראה, אתה צודק שפה למעלה, אתה רואה שפה למעלה כתבתי את זה אחרת. ואז זה מראה לך שכדי שאלה לא יתאפסו, צריך שבעצם אתה צריך איזשהו הבדל במטריקס אלמנטס. כאילו, אז אתה צודק שזה כאילו אומר משהו על המערכת. כדי שזה לא יתאפס, בוא נראה. כדי שאלה לא יתאפסו אחד עם השני, אז אני מחליף M ב-N.
מה יש פה? אני מנסה שלב מה המוטיבציה.
מה המוטיבציה שלהם?
כן, כן.
לא, יש פה בטח תרגול שמתחיל ב-6 או משהו.
כן.
אנחנו יש לנו את הכיתה עד 6. אבל יש הרבה סטודנטים שמישהו מה, אני לא יודע למה, נורא אוהבים להגיע מוקדם. עושים את התיק.
אז כאילו...
לתקוע דגל.
כשיש איזה 100 סטודנטים בקורס, אז כזה...
אז זה שווה.
אם אתה שם, אתה לא ממש בהרצאה.
דרך אגב, אני זוכר את זה, זה היה נורא מעצבן אותי, שהיה בתואר ראשון כאלה, כאילו שהיו שומרים לכל החברים שלהם. אז היה צעיף פה, עיפרון פה, דף נייר פה, מחברת פה, תיק ריק פה.
כאילו גם שאתה עשית תואר ראשון, או שאתה לימדת תואר ראשון?
לא, זה כשאני עשיתי תואר. ואז הייתי בא, אני לא רואה את זה פה, אבל אולי אני צריך פה.
לא, זה קורה. אבל זה קורה יותר בשנה א', יש יחסית הרבה סטודנטים.
גם יש את הקטע של הזום, נראה לי, זה שינה את הכללים.